All right, we will go ahead and get started. My name is Nathi Rodriguez. I'm really excited to be with you here today and with James Tanton for Quirky Fun Multiplication. I am a former math teacher and currently lead the professional development for Mindsets Learning. So I'll go ahead and introduce Dr. James Tanton as people keep rolling in. I see Anne from Illinois, thank you. Dr. James Tanton earned his PhD in mathematics from Princeton University. He is the author, he's an author, consultant, and ambassador for the Mathematical Association of America in Washington, D.C., chair of the Advisory Council for the National Museum of Mathematics, and founder of the Global Math Projects, an initiative to transform the entire world's perception of what mathematics can and should be. This program has now reached over 6 million students and teachers across the planet. And James has taught mathematics both at the university and in high school institutions. He advises on curriculum, consults with teachers, and gives demonstration classes, lectures, and professional development sessions across the globe. James is also the recipient of a Joint Policy Board for Mathematics Communication Award for 2020. And although James sounds like a very serious scholar, James also knows how to make math fun, which is why he's here with us today. All right, James, so I'll let you take it from there.
And what a joy to be here today. Thank you. So let's see. I know what we should do. Okay, some people already know me. So someone knows the Global Math Project and all sorts of things. But okay, I think we should start today with an actual salute to mathematics. So I wonder if I could see everyone. No, I can't. All right, I will just trust you're going to be able to do what I'm doing. But I think some people who already know me might know what I'm about to do. But there is an actual salute to joyous mathematics. It's actually the international salute to math, because it truly is known all across this planet. So to start off today, let's do a salute to global math. Someone loves global math. Here it comes. All right, so before we start with our quirky multiplication, I think you need to put down all your drinking cups down, coffee cups down, pencil papers down. You need your arms completely free. So make your arms free, and you go as follows. Hang on, I need to get something out of my screen so I can see myself, but I'm doing it correctly for you. Here goes. All right. The international salute to mathematics begins as follows. Arms out front. Make your hands look very big on the screen. Then it goes right hand over left hand. That's the hard part. You tell by my wedding ring I'm not cheating. It is my right hand over my left hand. Then it goes palm to palm. And then the salute gets weird. You wiggle your little fingers. Then you wiggle your thumbs. Then you wiggle your little fingers again. And then when you're ready, just come on back. Whoa, whoa, whoa. Maybe I should do it again. So I'll do it again one more time. I'll do it from the side. Let's see how this camera works. I'll try it from the side view. Arms out front, right hand over left hand. There we go. Palm to palm. Great. Wiggle the little fingers. Wiggle the thumbs. Wiggle the little fingers again. And when you're ready, just come on back. Whoa. What do you think? What do you think? I can look at the chat. What do you think of that? Were you able to get it? Just type in yes, no, or question mark, or some emoji of some kind to let me know what you think about the International Math Salute. I cannot do it.
Yeah, I'm seeing I cannot do it. Neither could I.
I know, it's a strange salute. Welcome to the quirky world of mathematics. All right, so okay, then let me help you out. I'll be a good guy here. I cannot do it yet. Oh, there's the growth mindset. All right.
Yes.
Okay, so let me help you out. I know this seems strange and quirky and weird. What's it got to do with mathematics? But actually, this illustrates a very deep mathematical principle that mathematicians use all the time. In fact, it's a great life skill. I've given you a problem. I've got a problem with how to do the salute. In fact, I'll give you a bit more than that. You've got a problem right now, and you know what the solution's meant to be. So often when you're given a problem in math, and you know what the answer's meant to be, or you suspect what the answer could be, here's a very good strategy that mathematicians do all the time. It is such an obvious strategy that people forget to think it because it's so obvious. Start with the answer and work backwards. It's actually a really good mathematical technique and employ it here. So I'll give this half away. What we'll do is follows. Start with the answer. So the answer is this. This is like at the end. So you have to say to yourself, okay, where must this come from? How could I reverse engineer this? Well, you say to yourself, okay, well, it must have come from that. All right, so maybe you're copying me right now. I can't see you guys, but maybe you're doing it. So, okay, that feels pretty strange. Next, let's keep reverse engineering. Let's keep going backwards. Well, you must have come from that, palm to palm. Now, I bet that feels very strange, very different from what you first did. So I just started at the end, and we got to this really weird, funny feeling middle position. Very weird. I bet that feels very different. So I've half helped you. So here's what you have to do now. Can you now start at the beginning and somehow get to that same funny feeling middle position? Because now you know what the middle position is like. Can you get to it from the beginning? All right, so I've half helped you. All right, so here's the deal. Here's the deal. We have 22 minutes left together in our lives. If this is driving you bonkers over the next 22 minutes, at the end of today, feel free to just type into chat and just say, James, just tell me the salute is driving me bonkers, and I'll give it away completely because I'm a good guy. I will do that right now. But I bet you could figure it out if you just had the chance and the patience. Because it probably takes me I'm very slow at these things. It takes me a good week or so. Anyhow, but here goes. Let's talk about quirky multiplication. Multiplication that's quirky. Actually, what's this lovely? I actually gave a webinar for Mindsets a while ago with one really fun way to do multiplication. So we should actually really start this journey. So starters, go look at the previous recording of another webinar I did on fingers and toes to do multiplication. But let's now start with other quirky ways to do multiplication that's not in that webinar from last time. So I'm going to share my screen. I have to find the right program to share. It's that one. And hopefully right now you are seeing a piece of paper and a bunch of pens and my hand that looks deathly gray in this light for some reason on this camera. Okay,
yes, we can see it.
Yes. All right.
All good.
Quirky multiplication. So some of this stuff is out there. So here's one that's very popular. If you've probably seen it before, maybe, or if not, doesn't matter, we'll see it now. I call this line multiplication. Here's a strange way to do multiplication, if I can spell multiplication, with lines. I think it's also called Japanese multiplication on the internet sometimes, or Chinese multiplication, or some other Asian name, or some other country. But it goes as follows. Suppose you want to do, say, 21 times 32. All right. Now, in this day and age, if I really want to do 21 times 32, I'll just get it by smartphone. If my only goal is to get the answer, then smartphone's the way to go. However, if you want to do some quirky fun and do some thinking, here's a quirky way to do it. I'm going to look at the number 21, the digit 2, the digit 1. For 2, I'm going to draw 2 vertical lines. And for 1, I'll draw 1 vertical line. There's 2 and 1. For the digits 3 and 2, the next number, I'll make them horizontal lines. I'll do 3 horizontal lines for 3 and 2 horizontal lines for 2. Very weird. And then I'm going to count intersection points. For example, I see there's 6 little intersection points clustered right there. There's 3 little intersection points clustered right there. I've misaligned that one, but there it is. 4 little intersection points in this cluster and 2 intersection points in this cluster. Okay, so just count intersection points. And now do this really weird thing. Add up these intersection points diagonally. For example, there's 2 on this diagonal. There's 3 plus 4, there's 7 on that diagonal, and there's just 6 on that diagonal. I claim 21 times 32 is 672. Whoa, that's weird. In fact, we can do bigger ones. Let's do a bigger one. Let's do something like 331 times 12. Let's try it. 3 vertical lines for the first digit, 3 vertical lines for the next digit, 1 vertical line for the last digit, some horizontal lines, 1 horizontal line, and 2 horizontal lines for the digits 1 and 2. All right, so all we have to do is add up the intersection points diagonally. There's the diagonals. What have we got? 1, 2, 2. We've got 1 and 1, 2, 3, 4, 5, 6. That makes 7. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. And we've got 3. I claim 331 times 12 is 3,972. Crazy. That's insane. So let's do another one. That's my answer. When something's insane, do another one. How about something a little bit bigger? I was being nice to myself then. 341 times 23. All right, so here goes. 3, 4, 1 times 2 and 3. All right. Okay, I'm going to add up the intersection points diagonally. So there's 1 diagonal. Here's another diagonal. Here's another diagonal. Here's another diagonal. Let's add them up. Here goes. 1, 2, 3. 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 actually, because I miscounted. There's what, 12 there and 2. Oh no, 14 because I can't count. 14. That's my trouble. I'm a mathematician. That means I can't count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 there. And 1, 2, 3, 4, 5, 6, 6 there. Ooh, there's a weird answer. Now, those that know me know I do this thing called exploding dots. I have no trouble with this answer. I would say this answer is 6,1714. But that's, people don't like 14 tens. People don't like 1700. So, okay, 14 tens is really 4 tens and an extra 100. The answer is 6,1843. So people don't like 1800s, say, no, no, no. Make it 800s, and 10 hundreds makes an extra 1,000. The answer is 7,843. I bet that's correct. I bet that's correct, unless I miscounted. All right, all right. Your turn. On your ownsies, I want you to try this one. How would you personally handle this wrinkle in the works? 102 times 31. How would you do that one? So if you've got a piece of pencil and paper, give it a go and just write in the chat saying ick or fabulous or tricky or weird, some emotional word. And Nadi's going to read what some of the words come up with because there's a wrinkle in this one.
All right, I'm ready. Let's see. There's some thinking. There's a question about the lattice method. Am I pronouncing that? Might not be pronouncing that correctly, but.
Okay, I remember that. Okay, I'll take note of the lattice method. Yep.
Okay.
First of all, can you even draw this one? Because what's the issue with this one? It's that annoying thing. How do you draw 0 vertical lines? Or should you not bother? That's the issue. That makes us even extra quirky now. What do we do with this? But by the way, the answer is basically 100 times 31. So the answer should basically be 3,100. Actually, the answer should be, it's 100 times 31 plus 2 times 31. So actually 3,162. So I can see what the answer is going to be without actually doing any of this work. So whatever I draw should give the answer 3,162. Let's give it a go. Now, some people might just draw 1 for the 1, draw nothing for the 0s, great, and then just draw 2 for the 2. That's great. But then you might get an answer that's too small, because that actually kind of looks like you're multiplying 12 by 31. So you might think to say, no, I really need to keep track of no lines in there. So you might want to do a dotted line, or do some like line crossed out or something. And then that's really gets clear. It's 102 times 31. Now, if I kept that spacing correct, does it actually do the right thing for me? Here are the diagonals. That's 2. 2. Yes, 2. That's good. 1, 2, 3, 4, 5, 6. And technically, that's no intersection. There's actually technically no line there. So 6 plus 0 is 6. Yes. Technically, there are no intersections there. So it's nothing plus 1. Yes. And 3. 1, 2, 3. 3. Yes. Bingo. So it's kind of fun to think about what do you do with zeros all around the place. I guess you need the placeholders.
Yes, we have somebody that offered placeholder. All right.
Yes, placeholders. Excellent. So positional notation, place value system that we Westerners like to use all the time really needs us to keep track of place. Place matters a lot when we write numbers, and here it is. All right, so that's quirky multiplication number 1. I haven't explained why it works, but I want to show you 2 other ways to do quirky multiplication, because here's my other one. I call this second way school multiplication. And I want you to let go of what you know, because what I'm about to do is actually truly bizarre. Let's think of something like 37 times, let's do that. Let's make it 23. Let's be kind to ourselves. 37 times 23. Think about how bizarre this is. Now, when I was in school, I was being taught to read left to right in every class. You know, go to my English class, go to my other classes, always left to right, except math class. Because in math class, I was told to always do computations right to left, which is weird. So that's weirdness number 1 about this problem. Here's the other way. Here's what's also weird about this. You're taught to go last digits. 3 times 7 is 21. I want to write 21. You say, no, don't do that. You're not allowed to write 21. You have to write 1 with the 2 up there. That is bizarre. Bizarreness number 2. This is a really quirky way to do multiplication. Then I was taught to go 3 times 3 is 9. Okay, 9. I'm allowed to write 9, but no. Then I meant to add 2. Hang on, I thought I was doing a multiplication problem. I meant to add 2. Okay, so I now write 11. This time I am allowed to write 11. In fact, I do write 11. So before I wasn't allowed to write 21, but now I am allowed to write 11. Bizarreness number 3. Then just put in a 0. Why not? Bizarreness number 4. Then you go 2 times 7 is 14. You don't let me write 14. You just say 4 and put a 1 up there. Bizarreness number 5, or repeat a bizarreness number 1, whichever one it was before. Okay, then you go 2 times 3 is 6. And says, no, don't be confused about the 2 that was before. You should have been crossed out, silly fellow. 2 times 3 is 6. Add 1 to make 7. Whoa. Okay, that's bizarre. And then to finish off the problem, our multiplication problem, just end off with addition. Why not? 8, 5, 1. You have to admit, that is very, very bizarre. School multiplication is a quirky way to do multiplication. That is very odd. In fact, when you really think about this, most people don't realize it, but this is actually surprising. Suppose I did 23 times 37 instead. Now, we're all told it should give the same answer, but look at this method. It gives us totally different working. 3 times 7 is 21, 1, carry the 2. 2 times 7 is 14, 16, I'm allowed to write 16. So look, it already looks different. Those middle parts look different. Then you do a 0, 3 times 3 is 9, okay, 9, 3 times 2 is 6, I write that, I believe, is that right? Bingo. And then I add them up and I get 1, 15t, 8. So actually, it really is shocking that the middles look totally different, yet they give us the same answer in the end. That is shocking. If you actually think about that, that is bizarre. That is totally bizarre. Why should we be able to switch multiplication? Because we do long multiplication, the whole process is completely different, yet we get the same answers in the end. That is actually mind-blowing. But the trouble is with us adults, we are so familiar with this algorithm that we don't think it's bizarre anymore. We're too close to it to see how bizarre it is. For young students seeing this for the first time, you've got to admit, this is actually crazy. So I think that deserves to be called quirky multiplication as well. School multiplication is quirky because that is odd. So I guess I need to explain that as well. But before I explain that one, I want to do another quirky multiplication. And someone said lattice method. All right, I think I've seen this before, lattice method. Actually, I'll tell you, it was also very popular in England during the Elizabethan period. So it's also known as the Elizabethan method. So I don't know if you know that name in America, but I think as a kid, I saw it as the Elizabethan method because, I don't know, Australia is very Anglophilic. So to do something like 37 times 23, the example I just did, you do this. You draw a little diagram and you make boxes and you'll do 3 and 7. So instead of doing lines for each digit, I'll do boxes for each digit, 2 and 3. And I'll put diagonal lines in all the boxes, which is weird. Why am I putting diagonal lines in? I don't know. It's just being quirky. And the idea is you go through and do each little product you see. For example, 7 times 3 is 21, but you write 21 across the diagonal. Whoa. 7 times 2 is 14. You write 14 across the diagonal. 3 times 3 is 9. Oh, I need a 2-digit answer. Oh, so you write 0, 9 across the diagonal. And 3 times 2 is 6, so you write 0, 6 across the diagonal. And like the line method, you now add up everything diagonally. 1, I'm in trouble, 15, 7, 0. So the answer is 0,715t1. Oh, 10 ones is the same as 100, so it's really 851. Wow. Okay, so how am I doing time-wise? Because we now have 10 minutes to explain lattice multiplication, school multiplication, and line multiplication. We've got a lot of work ahead of us for 10 minutes. And plus I have to do the maths loop. My goodness, are we ready for it? Here's what I think multiplication really is. I think the best way to do multiplication is with area. Because actually, when someone says to me, 37 times 23, I'm actually a very visual creature. To me, that's saying, please work out the area of a rectangle that's 37 centimeters by 23 centimeters. Because to work out the area of that rectangle, what I have to actually do is do the computation, work out 37 times 23. So that represents the area of that rectangle. Now, I'm a mathematician. I'm a person of life. Like all mathematicians who live in life, no one likes hard work. Mathematicians don't like hard work. In fact, mathematicians work very hard to avoid doing hard work. No one in their right mind wants to work with the numbers 37 and 23. So say, no, I'm not doing it. What could I do to make my life easier? Well, it seems very natural to make this like, say, 30 and 7. Let's just split the rectangle up. And hopefully you don't mind my picture not being to scale, but I think the information is correct, like 30 centimeters and 7 centimeters. That's okay. Off scale, but you got the idea. 23, that's awkward. How do I split that one up? Well, my brain says, please, just make it 20 and 3, because that's so much nicer. Because now, all I have to do is work at the areas of the individual pieces, and then I can add up all the individual pieces, and I made the numbers nice to myself. For example, this piece is 7 by 3, it's 21. This piece is 7 by 20, that's 14 with an extra 0, 140. This piece is 30 by 20, that's 3 times 2, it's 6 with a couple of zeros, 600. And this one is 3 times 30, 90. And I can see the area is 600 plus 140 plus 90 plus 21. So what's that? 740, 840, 830 plus 21. Oh, 851. Bingo. So I love the area method. But look at this. this really was the line method in disguise. Suppose I did this problem via lines. I'd go 1, 2, 3, 4, 2, 3, 4, 5, 6, 7. So there's 37. I'd go 23, 2, and 3. All right. Well, that looks similar. I've got 30 and 7, 20 and 3. Now I've just got 3 and 7 and 2 and 3. In the line method, you work out how many intersection points there are. Actually, the number of intersection points is just going to be 2 times 7. The number of intersection points here, is going to be, what, 3 times 7 of them, 21 of them. The number of intersection points here is going to be 3 times 3, which is 9. And the number of intersection points here is going to be 3 times 2, which is 6. And I was adding up the intersection points diagonally in the line method, but look, there's the number 21. There's the number 21. There's the number 14. There's the number 14. There's the number 9. There's the number 9. There's the number 6. There's the number 6. I mean, that 6 really did come from 3 times 2, but I added a couple more zeros to it because I realized it was really 30 times 20 in disguise, which is what's happening here. This line method's doing the same thing. It just says, don't bother keeping tracks of the zeros, because I'm going to realize the real computation is 6. That's the key thing. But I will add it up as part of this diagonal as though it's part of the 100. So it's really 600, which is literally what you see in the area model. This one is really 7 times 20. So the actual computation was 14, but it's really 7 times 20 makes it 140. This one was really 30 times 3. So the actual computation was 9, but it's really 30 times 3 makes it 90. So these ones are all the 10s. That really adds up to what 14 and 90 is 230. Am I right? No, 9 and 14. Yes, 230. Great. And then 21 right there, because that really was 3 times 7. So what this line method does is actually, it is the area model. It just doesn't bother writing the extra zeros in because it knows that you will do your diagonal adding up, just like you do in the area model as we had hundreds, tens, and ones. So the line method is actually the area model in disguise. Whoa. And in fact, the lattice method is also the area model in disguise. Let me do it over here. It's actually the same thing. Again, it says, look, we're in the Elizabethan England. Ink is precious. Please don't waste ink by writing the unnecessary zero. Just write 3 and keep it in mind that's really 30. Write 7. Save some ink. Don't actually write 2 zeros. Save some ink. Don't bother writing 20. Just write 2. And then 3 there. And it says, okay, be bold, waste some ink. Do that instead. Right. Okay, so that's a little contradictory there. But, for example, look what happens. 21, this 3 times 7 that we write in the area model, well, we wrote it like this, 21. But we did that deliberately because what this diagonal is saying is we'll have 1 unit and 2 tens right in this box. This diagonal forces that 2 to go amongst the tens. Very clever. 14, we wrote 1, 4 like this, but it's really 140. It's really, 4 tens and 100. And what the diagonal has done for that is force us to do the carry right off the bat. Bump that one extra, those 10 tens up into the hundreds column. And it's done the carrying automatically for us. 3 times 2 is 606, but it's really 600s. There we are in the hundreds column, and so on, 09, bingo. We really got 30 times 3, 90, but it's in the tens column. So what the Elizabethan method is actually doing is forcing us to do the carries within the diagram, except you get extra carries with the 15 there and do some more carries afterwards. Whoa. Whoa. And how much time do I have? I have 4 minutes. Okay, 4 minutes. Because I want to explain the weirdest multiplication of all, which was school multiplication. School multiplication is the weirdest one of all. There it is. This is bizarre. In fact, you know what? I think what we teach is truly, truly bizarre, and I don't think we should teach it. If I was ruler of the math teaching universe, I wouldn't teach long multiplication. Because when do you actually do this in the real world? If you're going shopping and you have the store clerk say, I need to work out 37 times 23 cents for you, do not expect them to pull out pencil and paper and do this on paper. No one ever does this on pencil and paper anymore, except in school classrooms. If the goal is just to get the answer, pull out your smartphone. I have no objections to that. But I have no objections to teaching thinking, and this is about the thinking. This is about what's really going on. For example, let's look at that school multiplication approach. So when you say, you go, okay, right to left. All right, right to left. Everyone's right to left in maths. I don't know why. 3 times 7 is 21. I say, actually write down what it is, 21. Then go 3 times 3 is 9. But actually, realizing it's really 3 times 30 is 90. So actually write down 90. Please actually write it down. 2 times 7, it was really 20 times 7. Please actually write down 140. And 20 times 30, 2 times 3 is really 600. Bingo, there it is. It really is 600. It really is 140. It really is 90, and it really is 21. In fact, I say just draw the rectangle. Even writing it this way is unnecessary. But that is really curious. And then this addition at the end makes perfectly good sense. Of course, I want to add up the 4 areas like we did in the area model. I actually added them up. Bingo, and I get what, 851, I'm sure. Beautiful. But here's the thing. We teach students this. Is my screen working? Uh-oh, my screen is frozen. Oh, now you see. Okay, good. All right, we teach students this. And we've lost all the joy and beauty and the insight about what's actually going on. Though, look at this. What is 21 and the 90? If you combine them together, it's that 111. What's this 140 and 600? If you combine them together, that's 740. So actually, back in the 1600s, 1500s, 1400s, 1700s, when ink actually was precious, when ink was scarce, people said, look, let's not bother writing this out. We could actually use less ink. If we teach this idea, like doing those multiplications together, those ones together, combine them, that uses much less ink. We can actually get multiplication problems. All we had was pencil and paper back in those days. Let's teach everyone this way. They can still do the multiplication problems by the best technology at hand, pencil and paper, using very little ink, and life is good. So here we are, 400 years later, when we don't need the pencil paper method, when paper and ink are no longer scarce, we are still teaching this method. And often we teach without thinking. Now, I know things are better now. Things are much better now. We do teach the thinking behind this. My point is the thinking is this. In fact, the thinking is also this. In fact, the thinking is also this. It's all the same thinking. And you've got to love it because actually this makes maths joyous. In fact, I will gladly teach long multiplication, don't get me wrong, because it's a beautiful opportunity to teach wondrous, joyous thinking. That's the point of maths, in my opinion. Because actually, you know, it actually teaches life skills. The willingness to pursue problems and make sense of problems and persevere with them is what life is all about. All right, so I have 30 seconds left. Would people tell me in the chat, would you like me to do the math salute one more time and give the answer away? Just say, give answer away, and I will. Yes.
Yes.
Yes. Yes. All right, here goes. All right, here goes. I'm going to give it away. So the trick is arms out front, right over left. Now, what most people do when they go palm to palm is they twirl their thumbs in opposite directions and then go wiggle, wiggle, wiggle. Thing is, I'm not doing that. I'm being strange. I'm actually doing this, twirling my thumbs in the same direction, in parallel to my left. I'm twirling my thumbs in parallel to my left, which feels very strange, but that makes you have set to come back. So here's the feeling. Imagine you're holding a big red rubber ball. It has to be red. And imagine you just turn the ball upside down, and then clasp your hands. That's that funny feeling middle position, because now you're ready to just come back. So what I'm really doing is turning a ball and coming back. So I've got to do that with my wrists touching. So here goes. Wrist touching, thumbs in the same direction as though it was a rubber ball, but it's kind of weird. To the left, make sure your thumbs don't get in each other's way. Wiggle, wiggle, wiggle. Now you're ready to come back. Whoa, that was fast. All right, if you're like me, it'll probably take a couple of weeks to figure out what's going on and master it. But once you've mastered it, then you are holder of the sacred knowledge of the International Math Salute, and it's beholden upon thee to then share the Math Salute with the world. And if you think I'm just being strange and quirky and I'm just making this up for today, Google International Math Salute and you will find it. You'll find people in Belgrade and in Tokyo and Australia and Tanzania doing the International Math Salute. All right, on that note, I'm going to say thanks for coming. Quirky multiplication. Check out the previous recording, which has yet the other fingers and toes multiplication method that uses negative numbers actually. It gets quite deep mathematically. And Mindset's actually got a good little activity on negative numbers at hand as well. So everything's robust, everything's complete, everything's together. Thanks so much, everyone.
Thank you, James. Thank you, everyone, for joining us today. You can connect with James at tanton.math@gmail.com or follow him on social. And for those of you that attended today's webinar, we are offering a free back-to-school 3-month trial of Mindsets. Mindsets is an award-winning instructional platform that offers authentic, project-driven challenges where students get to use their math skills to solve real-world problems, and the challenges are standards aligned. All right, thank you so much. If you have questions for me, please email me at hello@mindsets.com. Thank you, everyone. Bye.
Thanks all. Bye-bye.